Hello, and welcome back to a video series on MAC 1105 College Algebra. This is guided notes number 9 in the series on section 3.1, the definition of a function. We can think of a function as a kind of rule that takes one number, an input number that we usually signify with an x, and it gives us one output number, which we signify as f of x. This is playing the role of y when we use dependent variable, independent variable notation. You could think of this as the output when you plug in x into a set of rules called f. Even if we don't have an explicit set of rules, there's a lot of ways that we can depict a function. One is to show, if there's a small number of inputs and outputs, where each input goes. Here, 1 goes to 4, and so does 2. We would write those two facts like this. Now 3 goes to 5, which we would write like this. Notice that we're changing the thing inside the parentheses, and f tells us what that means, what the output should be given that input. We could also list these with coordinate pairs, or we could list these with a table, which implies, as we will soon see, that functions can be graphed. A little bit of terminology. The numbers that we plug in, the values that we have a rule for, the x values, are called the domain of f, which we sometimes write this way. And the values that get used, in this case 4 and 5, the output values, or the y's that get hit by the function, is called the range of that function, which we sometimes write this way. Now notice that 6 is not in this range because there is no value that gets mapped to 6. We call this whole set the codomain, but that's not a piece of terminology we're going to use very much. But you need to know that the range might actually be just a proper subset of this larger space. Sometimes it's the whole space, sometimes it'll be the whole number line, and other times it will only be a section of that. The same thing is true with the domain. Sometimes there are reasons why, given a certain rule, we might not be able to plug certain numbers in. We'll see a lot more about that soon. In the meantime, let's start it on the guided notes. Question 1 asks us about the domain and range of a relation that's specified by these coordinates. Now, a relation is sort of a more general thing than a function. All functions are relations. Relations are rules that tell me about how an input would be related to a certain output. But let's go back to our function definition for just a moment and recall that there's this one very important underlying feature. It says that when we are given an input, it gives us one number as an output. This doesn't mean that things can't repeat. They're allowed to repeat as y values, but if they are the same x value, we cannot draw a second arrow that takes us somewhere else. We cannot give two outputs for a given single input. Such a thing would be a relation, but not necessarily a function. And that's precisely what's going on here. The input slot, or the first slot, are all -5s. And that's a problem, because we now have different outputs for the same input -5. If you have more than one output for a given input, it is not a function. It is merely a relation. And I want to stress this other example if the situation was completely reversed, if the domain and range had been interchanged, my roles of input and output switched. This would in fact be a function, because each input, 4, 3, 2, and 1, only has a single value assigned to it. There isn't another 4 over here somewhere. The fact that they're all -5s isn't really a problem in terms of whether or not it's a function, because all the function has to do is be assigned one output for a given input. Okay, so let's move on. How can we determine that this is a function based on the rules? Well, they want us to define a function y in terms of x, and that means solving for y. Notice when I solve for y here, I get an expression which only gives me one value when I plug in x, a single value, right? Multiply by 2, it's still a single value. -5/2, it's still a single value. And so we only get one y for each x here. So this is indeed a function. Same thing here. If I square something, I only get a single value. And if I subtract that from 36, again, it's a single value. So this is in fact a function. Here's an example of something which is not a function. When we go to solve for y in this case, we have to apply the square root property, which says that if something squared is equal to something else, that is going to be equal to plus and minus the square root of that something else. We need a plus and a minus root if this is an even power. And so we wind up with two answers. If I plug in a single value of x, we wind up with two answers as an output for y. And this brings up another kind of restriction on the domain of the values of x that we would be allowed to plug in and the values of y that we would expect to pop out. Here I've graphed the function. Let's use a graphing utility to see it a little bit nicer. So here I've opened Desmos and I've just typed in our expression into the input here. And we can see that this is actually a pretty common figure. It looks like a circle. There's a good reason related to the Pythagorean theorem that this should be the case. Maybe we can talk about that later on in this chapter. But for right now, let's notice that there's actually only certain values of x that we see appearing on this figure. It only appears between -3 and +3. And likewise, my y values only appear between -3 and +3. Why is this happening? Well, going back to our equation, we see that if I picked values larger than 3 or smaller than -3, this would wind up being a negative difference on the inside here. And that would make the square root a complex value. If we're only interested in graphing real numbers, x and y, then these complex values are omitted. And in the graph, we can see that. We can see that if I go outside of this interval from -3 to +3, I don't see any graph. And that's because we are graphing a real number into another real number. If we could somehow graph the complex numbers, we might see a different kind of shape. And this will limit the domain and range of this relation. And this relation is not a function. We can see that if we plug in, let's say, -2, there are two values that pop out, a +1 and a -1. And that's going to rule out this being a function. We'll see very soon that there is a test called the vertical line test that would intersect this circle in two places and rule it out from being a function. Here we have a graph of another function. We can tell it's a function because if I plug in a single value of x, minusing 1 and taking the principal root, we can only get one value back for y. Let's talk some more about domain and range in this case. We'll learn very soon about transformations of functions and how this is actually a right-shifted square root function, right-shifted by 1. But in the meantime, we can see right away that if I plugged in something 1 or greater, I would get a real number back as my square root. And if I plug in something less than 1, it's going to give me a complex number because I'll be taking a square root of a negative. We're ruling those out in this conversation. And so we would say that the domain of this function is going to be all of the values from 1 up to infinity. Now, what y values are hit? Well, the y values begin at 0, and this rises and widens forever, and so all of the y values from 0 to infinity would also be hit. And this tells me about the domain and range of this function. We know it's a function because every x value only has one single y value above it. Here we've been given a function h of x, and we're asked to calculate certain values. All that would be required in order to do this is to replace our x with whatever we see inside the parentheses here. For example, in this function, we have -3 times the square root of -7 minus x, then plus 9 times x. So everywhere I see an x in this first problem, I'm going to put -71. Now, we could do this by hand. We could evaluate it on a calculator. I'll do one of them by hand, and the rest I did on a calculator. So we would have to add 71 because we're subtracting a negative. This would give us 64, whose square root is 8. Multiplying that by -3 would give us -24, and adding that to -639 gives 663. Our 639 just came from 9 times 71 here. Likewise, with these remaining examples, all I'm doing is replacing x with a -43 because that's what's in the parentheses. If we do that, typing all this carefully into the calculator, we'll get -405. If I plug in -32, I get -303. And here we have something a little different. Now we have an expression x minus 7. The entire expression x minus 7 needs to be put in wherever we see a x. So when I put that in, I'll have to distribute my negative sign. This gives me some 7s I can cancel. And distributing my 9, we get 9x minus 63. Carrying this down, I'll have -3 times the square root of minus x plus 9x minus 63. And none of these are like terms. I can't really simplify this radical. This is where we're going to have to stop. On the other hand, for the last one, when I plug in x plus 4, distributing this and collecting like terms, I wind up with -11 minus x. that's it. There's really nothing else that we could do to simplify this expression. These aren't like terms, and so we'll stop here. This next one proceeds in a similar fashion. All I need to do to evaluate these is to replace my x's with the number that's in the parentheses here. So f of 0 is equal to negative 6 times 0 squared plus 8 times 0 plus 6. That's pretty easy to see it's a 6 because these two terms just go to 0. With a minus 5, same idea. We want to evaluate minus 5 squared, which is 25, and minus 5 times 8 is negative 40. Combining my numbers here, I wind up with minus 184. Same deal, 2 squared is 4, 8 times 2 is 16, 16 plus 6 is 22, and minus 6 times 4 is minus 24. Minus 24 plus 22 is negative 2. Again, we have some expressions to evaluate. This is called composing the function with another function. We've plugged in essentially another simple function into f, and so all we have to do is replace our values of x with this particular function, x minus 5. So we do that, but this squaring is going to require us to FOIL. We can use the perfect square formula to do that quickly, and distributing and collecting like terms, we wind up with the following. Plugging in minus x is even easier, because squaring will get rid of this negative sign and just give me x squared. Here I need my minus sign to come out front, and the 6 doesn't have anything to do with it. So this is our function. Here we're given a rational function for g of x. It's x divided by x minus 7. Again, whenever you have something in these parentheses, you simply need to replace that wherever you see an x and simplify. So here I've done that for negative 9. We want to do that again for minus 3. There we go, we get 3/10. What about 8? I put that over here. 8 over 8 minus 7 is just 8 over 1. That's just 8. And now, plugging in this expression, this function itself, x plus 9, into the function g of x, we get x plus 9 over x plus 9 minus 7. Simplifying, we get x plus 9 over x plus 2. That can't be simplified anymore, and so this is where we would stop. For the last one, we're going to plug in 4 over t everywhere that we see an x. And that's what I've done here. This is fine. This is correct. We could probably make this a little bit simpler, though, if we followed some fraction rules, right? I can combine the two things in the denominator by getting them to have like bases. T over t will turn this 7 into 7t over t. Then I can subtract the numerators and evaluate this compound fraction divided by a fraction by flipping the denominator and multiplying. This seems to cancel the t's, and we wind up with g of 4 over t is 4 over 4 minus 7t. I want to point out that we still need to keep in mind that t can't be 0. T is not allowed to be 0 here, or we're actually plugging in something undefined. It seems to cancel right here, but that doesn't matter. If something cancels, if it's 0 over 0, it doesn't cancel. It's actually undefined, and so we could only make this cancellation in the event that t was not equal to 0. It now appears that t equal to 0 is a perfectly fine value to plug in. You would just get 1, but that's not actually the case. This is still undefined in the case where t is equal to 0. It's still omitted from the domain of our function. Try to keep that one in mind. Okay, here we're going to get into something I alluded to before about the vertical line test. Recall that we said a relation is a function if it gives me one value back for each value in the domain. Now, if I pass a vertical line along the curve, we see the one value that I get for every input from the domain. But if I come into a place where there are two outputs, two numbers, where the vertical line intersects, then this would tell me that this relation would map -1 both to 1 and to -2. That's two outputs for a given input, and so this is not a function. Over here we have a line. It intersects the vertical line in only one spot at any given time, so it is in fact a function. Here we have an ellipse. If I pass this through the ellipse, we could see that it hits the ellipse in two places almost everywhere, and so this is not a function. If we pass it again through this diagonal line, it hits it in only one place at any given time, and so this is in fact a function. Here we have some more functions. This sinusoid still only hits the side of my ruler here in one place at a given time, and so it is a function. The same thing with this cubic function here, where it seems to go up and down, but at any given time, the vertical line only hits it once. So there's only one output for every input of x. Here we have something a little bit more complicated, where it would seem that we have several different rules being applied in different places. This looks like a constant, this looks like a non-constant line, and this looks like some strange wiggly curve. So is it a function? Well, I mean, that's not part of the question, but let's answer that question. Yes, it is. If I pass this along, even at this place like -2, where it seems to have some kind of two values assigned to it, we can see that one of those values is an open circle and the other value is a closed circle. So actually, there is no value here. There's only a value down here. And the same thing is true at this point of x equals 1. We aren't going to actually map to this circle. We're only going to map to the closed circle. So this is indeed a function. How do we evaluate the function? Well, the first two questions are pretty easy because they're giving us x values and asking us what that gives us. If I look at -2 and I go here, well, actually, here is an open circle. Here is the closed circle. So this is where we would send -2. We'd send it to -4. Same thing with 1. This is an open circle. We don't send it here. We would send it to 3. And this is a bit more complicated of a question because of what they've seemed to have drawn right here. They said, where is it -4? Okay, well, it's definitely -4 at -2. That's true. But it also seems to be -4 at -5 and -9. And does this continue? I mean, there's no indication that the graph stops here. It seems to just maybe wiggle forever in this up and down kind of fashion, which would mean there's a -4 at -13, another 4 units later, and -17, and so on. Are we supposed to list them all? I actually don't know. I'll have to check on this homework problem and see if that's the case, because I don't think that's a very fair question to ask you at this time, especially if you don't know what the properties of this very conspicuous looking curve are. Let's check in on a little word problem here. It says a company manufactures scooters with a fixed cost of $105,000 per month, and each scooter costs $115 to produce. What is the company's total cost in terms of the number of scooters? And write this down and interpret C of 80. Okay, well, your cost in terms of X, the number of scooters, is 105,000 plus 115 times the number of scooters we've produced. This is our fixed cost plus our variable cost times the number of scooters that we produced. Each one costs $115. And so we would need X times 115 to get the cost of producing a total number of scooters X. So what is C of 80? Well, this is going to be the cost necessary to make 80 scooters. We would take 105,000, the fixed cost, and add $115 per scooter times 80, the number of scooters, to get the total amount of money that I would spend, which is $114,200. Here we have an example of a piecewise function similar to the one that we looked at graphed just a moment ago. The idea is that we are given different rules that correspond to different intervals. If x falls into this interval, namely if it's less than 0 or if it's negative, we're going to want to do this to it. We're going to want to take 7 times it minus 2. Likewise, if x is greater than or equal to 0, we're going to want to take -7 times it and minus 8. So in order to figure out what these are, we just need to decide what interval they fall in. -4 falls into this first interval, so we apply the first rule set to get -30. 0 falls into the second rule set, so we apply the second rules to get -8. And 4 falls into the second rule set, so we apply the second rules to 4 in place of x to get -36. Here we have the exact same procedure. It's just slightly more complicated because there are more rules. A piecewise function only needs to have some finite number of rules associated with it, but we're going to look at mostly things that have either 2 or 3 rules when we look at a piecewise function. Now, this first one asks us what happens to -5. -5 is in this first rule set, and so we just plug -5 into the first rules to get 0. Same thing with -2. It falls into the second rule set. It's between -5 and -1, so we plug that into the second rule set to get 21. And proceeding as follows, right? We take -8. It goes into the first rule set, so we apply those rules to it to get -8 minus 5, which is +3. All the last ones, 6, 8, and -1, they all fall into this third rule set of being greater than or equal to -1. So we want to take 4 times that number, minus 3 from that, and that's our answer. 4 times 6 minus 3 is 21, 4 times 8 minus 3 is 29, and 4 times -1 minus 3 gives me -7. Here we have an interesting problem where they ask us to figure out the composition of this function with the term a and with the term a plus h, and then to take those two things and construct this expression out of them. This is a very important expression in calculus used to abstract the notion of slope. But for now, all we have to do is follow the instructions and see what we get. What is f of a if f of x is 2x plus 7? Well, I just replace x with a. That's all I have to do. What about a plus h? Well, x needs to be replaced with a plus h, and I encourage you to put that in parentheses so that you know to distribute the 2 to both terms. Now, what happens if I take and minus those 2 from each other and divide by h? Well, the first thing that you might see after distributing the negative sign is that we have a lot of cancellation going on. We have a 2a and a minus 2a, we have a 7 and a minus 7. In fact, everything that doesn't have an h term associated with it cancels to 0. Then we have 2h over h. Well, h divided by h is just 1, and so we're just left with a 2 here. Finally, we have this other form of the difference quotient that we'll be looking at. They say evaluate this when c is equal to 7. So we're actually going to replace c with minus 7 in each of these, and I think that will work out to just give us numbers and look a little bit simpler. F of x is just what they gave us, x squared plus 3x. There's not a whole lot to do there except copy it down. But what about if I plug in minus 7, which is what they told me c was? Then I'll have to square it and take 3 times it, which gives me 49 minus 21, which is 28. Now they ask, what is the difference of those two things? Well, if I take a look at that difference, right, and drop these sort of purely organizational parentheses, I actually get a polynomial, and it's a polynomial that factors. Not only does it factor, I get x plus 7 times x minus 4. And they ask us now to look at that difference divided by x minus c. But x minus minus 7 is x plus 7, which was one of my factors. If I have a factor divided by another factor, they cancel to 1, and we just get this x minus 4 term. It is interesting that we wind up with this cancellation here, where a difference of function values produced a factor that canceled the difference of input values. If you make it onto calculus, you'll see why these last two expressions are so gosh darn useful when it comes to describing change and rate. All right, that's going to do it for this video. Thank you very much for your patience and have a great day. Good luck with your studies. I'll see you in the next one.